if we look at this one, the IQX of humans is approximately normally distributed with a mean of 100 and standard deviation of 15. Compute the probability that a simple random sample of size 10 results in a sample mean greater than 110. So this is different than just saying, suppose that a random person has an IQ of 110. If I were just finding one person and their IQ greater than 110, it would just look like this. But I want the sample mean. Sample mean is X bar. So I'm asking for my X bar to be greater than 110. So not just for one person. For the 10 people I take, if I find their average, what's the probability it's bigger than 110? We have to convert this into a Z. Now we know our formula for Z is X minus mu over sigma. So I need the mean and standard deviation for my variable, which is X bar. These right here are the mean and standard deviation for the variable X. So for X bar, the sample mean, what is the mean of X bar? 100. I told you yesterday the mean of X bar is the same as the sample mean. Then the standard deviation of the sample means would be remember, if you have forgotten, look on your formula sheet. We are in chapter 8, and they are right there. So if I plug this in, my X bar is 110 minus the mean of X bar is 100 over the standard deviation of X bar is 15 over radical 10. So if I plug that in, I guess probability Z is greater than 2.11. Okay, remember your table, we can use our normal table because it's normally distributed. The table tells you the probability less than, so for greater than you do 1 minus. Then we read that 2.11 is 0.9826. We get 0.0174. So very low probability that in my sample of 10 people, I will have an average IQ greater than 110. So the only new piece here is if I'm talking about the sample means, you have to find the mean and standard deviation for that. Then you're doing it like the normal problems from the last chapter. Any questions there? Okay. Let's consider the probability distribution. So probability distribution, that's when you list the outcome and the probability for rolling a fair die. So fair die means 6-sided. So I want all my options and the probability. So if it's fair die, you can roll a 1, 2, 3, 4, 5, or 6. What is the probability of each?
6.
Okay, that's probability distribution. Let's graph this to decide if it's normal. If it's normal, what should the graph look like?
Bell shape.
The bell shape. Okay. So if I graph this,
So is this gonna be like one of the box ones or whatever?
the probability of getting a 1 is 1/6. Probability of a 2 is a 1/6. 3 is a 1/6. 4 has probability 1/6. So does 5, and so does 6. So what is the name for this probability distribution? What do we call those? 7.1.
Uniform density function.
This is a uniform distribution. So it is not normal. Now, rolling the dice itself is not a normal distribution. However, let's say I wanted to roll the dice over and over again and calculate the sample mean. If I were to roll the dice 200, or if I wanted to get 200 samples of size 4, so in other words, I'm going to roll the dice 4 times, calculate the mean, then that's 1. And I do that 200 times, so I have 200 averages. If you graph it, the distribution of the means looks like this. What is that? What does that look like? That looks a little more normal, doesn't it? This one, if I did 10 dice at a time, so I'm going to roll 10 times, get the sample mean, and repeat that. Then it looks like this. If I did 30, so roll it 30 times, get the sample mean. All of these look normal, and is it getting more or less normal as I go on? Yeah, this is getting closer and closer to being normal. You know, I see this one kind of follows it a little better, and this one is even better. So actually what happens, even if the original distribution isn't normal, the sample means can be normal. And it depends on the size of our sample. So the big thing here is this one. We talked about that top point yesterday, how the means of the sample mean is the same as the original. The shape of the sample mean becomes approximately normal as the sample size increases. So even if the original data is not normal, if you look at the sample means, it will become normal as you take larger sample sizes. This actually has a name. It is called the central limit theorem. The big thing you need to know, regardless of if the original is normal or not, we will assume the sample mean is approximately normal if the sample is 30 or more. So if it's less than 30, you would have to know that it was normal to be able to use your normal table. If my N is 30 or larger, I can use the normal table whether or not I told you that the original was normal. You want to write down that magic number 30 because it's going to come up. You're going to see that on tests and quizzes. You have to know if it's not normal, you need a sample of at least 30 to assume it is normal. And then I'm done. So suppose that the mean time for an oil change at a 10-minute oil change joint is 11.4 minutes with a standard deviation of 3.2 minutes. If a random sample of n equals 35 oil changes is selected, describe the sampling distribution of the sample mean. Your homework is going to ask you to describe this. What it's asking for is the mean and standard deviation of the sample mean. So if I say describe the sampling distribution of the sample mean, those are the things I'm looking for, the mean and standard deviation. Okay. So the mean of X bar would be what?
11.5.
Standard deviation of X bar is
3.2 over the square root of, is it 35?
Mhm. You could leave it like this. If you wanted to change it to a decimal, you can. As a decimal, that is like 0.54899. Sorry, 0.899. B. If a random sample of 35 oil changes is selected, what is the probability the mean oil change time is less than 11 minutes? So I am asking you for the probability that the mean, x bar, is less than 11. Now, if we know it's normal, then we can change it to a z. Have I told you anywhere that this is normal?
No, but it is 35.
Okay. So since n is greater than 30, so it is approximately normal.
Well, we have to write that on quizzes and stuff, like why we did it normally, or
I think
You
we just
might,
have
I
to
might ask you,
acknowledge it.
most of the time you might just need to know, but I might say, okay, let's assume the sample size is 15. Then what do we have to assume to use the normal approximation? So if my sample size is 15, it would have to be normal to use it. If I said the sample size is 50, do we have to assume anything to use normal? No. So I might ask a question more along those lines.
So what do we do if it's not?
Then we can't do this. We would have to figure it out a different way. Okay, so because my n is big enough, we can assume it's normal, so we can change it to a z. So you do your x bar minus the mean, 11.4, over the standard deviation. Now we need to round our z to 2 places because that's all the table goes to. So if my z is negative 0.74, less than just means I am reading from the table. And we get 0.2296. Any questions there?
So will we have it not normal or normal?
Probably not. Because we're basing everything off the normal
Yeah,
distribution.
so just like not normal.
I might just ask, is this normal or not? I wouldn't ask you to find the probability if it's not. Okay, last example. The mean weight gain during pregnancy is 30 pounds with a standard deviation of 12.9 pounds. An obstetrician obtains a random sample of 35 low-income patients and determines their mean weight gain during pregnancy was 36.2 pounds. Does this result suggest anything unusual? So to decide if this is unusual or not, we need to find the probability. What is the definition of unusual?
Less than 5%.
Less than 5% is considered unusual. Okay, so I need to find the probability that the mean, so x bar, was 36.2. To do that, let's do the probability that it's greater than or equal to 36.2. The normal distribution, we can't ever find where it just equals a certain number. We can do greater than, less than, or in between things. I can't just do equals.
So if it says that one, do you always do greater than?
Yeah, because I'm just trying to find out if this is unusual. So since this was more than the average, I would look at the greater than. Okay. What is the mean of, well actually, did this say it was normal?
no, but it has a sample of 35.
Okay. So n is 35, so that tells me it is approximately normal. Alright, so then we can change it to a z. So we need the mean and standard deviation for the mean. So the mean would be the same as the original, which was,
No, that's the standard
standard deviation of the sample means would be 12.9 over the square root of 35, and you're welcome to convert that to a decimal if you prefer. So I need the probability z is greater than or equal to 36.2 minus 30 over my standard deviation. So I get z to be greater than or equal to 2.84. How do we do greater than from the table? 1 minus. Okay, at 2.84, the probability is 0.9977.
So it's gonna be
There is only about a 0.23% chance, so not even a full percent chance that this happens. So the question then, does this suggest anything unusual? Yes, absolutely. What that means is either our sample was poor, so in some way we picked a poor group of people to use.
They were literally 4.
Sure. Or it could mean that the mean weight gain for the low income group was higher. So we would have to do more to figure out which of those cases it is. But we know that's unusual, so either it was a result of the sample we picked or our assumption that the mean weight gain for that group is the same would be false. All right, any questions, Mike? So we have a lot of time left, and you have 9 homework problems. So you've got the rest of the hour to work. This is due tomorrow.